So we've been talking about our three basic AC components: resistors, capacitors, and inductors. And they are what you might call two-wire components. They have two connections, and kind of an in and an out. But a transformer is slightly more complicated. A transformer is basically two coils that are intertwined. And the intertwined part is the fact that they share the same magnetic field. So you had a transformer that you built in lab this week that was basically a rectangle, something like that. And then connected to one side was a coil. And then connected to the other side was a different coil. And hopefully, I've made it look like the number of loops of wire on the red side is less than the number of loops of wire on the blue side. We don't always get a chance to draw these things to scale. So this would be a power source connected to there. And then over here, we would connect a load to that side. And in the lab today, not today, but this week, you saw that the iron core had a big effect on the transformer, that it really increased the amount of voltage that you could measure on the load side of the transformer. And it really serves two purposes. One, it increases the magnetism inside the coils. So there's a quantity called the relative permeability. And that is a scaling factor for the magnetic field inside the transformer. The relative permeability of transformer metal is somewhere around 1,000 or 5,000. So let's just call it 1,000 for nice round numbers. So that helps the transformer do its thing a little bit more efficiently. It affects the quantity called inductance that we talked about in the past couple of classes, and I'll show how that comes about. There's one more thing that the iron core does. It redirects the magnetic field around in that big square loop of the core. So it's what makes the magnetic flux the same everywhere. So the magnetic field is everywhere and the magnetic flux is everywhere. Remember, there's an easy relationship between magnetic field and magnetic flux. the flux is equal to some field times an area. And then we could put a cos theta in there, but that is really just 1 because basically the magnetic field in this case is going straight through the area. So theta is 0, so cosine theta is 1. And this is the per wire loop flux. As it turns out, the magnetic flux formula that we've been using, which is flux is NBA cosine theta, or NBA usually. We usually don't have to worry about the cosine theta. Includes the number of loops of wire in the formula. And with transformers, it's usually easiest to pick out the number of loops of wire in any given coil as a separate thing. So you could say the flux of a coil is equal to the N of that coil times the flux of a loop. So each time the wire is looped around the core here, it increases the amount of flux that that particular coil sees. And we do care about the flux because changing flux makes voltage. So there are, of course, 2 sides to the transformer, 2 coils in the transformer. The primary is the side we attach to the power source. That's the input of the transformer, which might be the output of a wall outlet. It might be the output of a generator. You attach the output of your power source to the input of your transformer. And what the voltage does in the primary side of the transformer is it limits the amount of current that flows. Think back to Ohm's law, where the voltage of a resistor is I times R. The resistance basically generates that voltage when you put current through it. And then that resistance limits the amount of current that flows in your circuit. So if you attach a big resistor to a battery, you'll get less current because the resistor's generating the voltage sooner. And that is kind of what the voltage in the primary side of the transformer does. It's in parallel with the voltage source. So it's going to be equal to the voltage source. The power source. Because they're in parallel with each other. So we have a power source and then the primary side, and they're connected at the top end and they're connected at the bottom end. And when you have 2 things that are connected together in 2 separate places, they are in parallel with each other. So the actual amount of voltage is determined by the power source, but it does serve to limit the amount of current that flows. So when you plug a transformer into the wall, it's not going to have current flow as if it's just a plain wire. If you plug a wire into the wall, then what's going to happen is so much current's going to flow that it's going to start vaporizing your wire. It's going to make a lot of noise. It's going to make a flash. It's going to evaporate wire. And last I heard, it's probably bad to have evaporated copper hitting you in the face. So generally, you shouldn't be plugging a straight wire into a wall outlet. Your wire has to be attached to some device that limits the amount of current that flows. And a transformer can do that. It does do that. And then there's the secondary side. And in the secondary side, the transformer generates voltage that ends up attached to the load. It ends up powering the load. So the transformer allows the power source and the load to operate. The power source provides the energy, and the energy gets to the load, but they aren't directly connected to each other. So the red part of this circuit and the blue part of this circuit are not directly in contact with each other. The wires are insulated from the actual iron core of the transformer. The only thing that the red and blue coils share in common is the magnetic field. Now, in general, it would be very difficult to calculate the voltages and currents in the two sides of the transformer. On the primary side, we know what the voltage is because we connected it to the power source. But to calculate the current, we would have to know the inductance. And unfortunately, inductance is not really a quantity for a transformer that's being used. Inductance is a property of an inductor, which has two wires. And a transformer has four wires, two on each side. So we'd have to go back to the relationship between current and magnetic field and magnetic flux, and then generated voltage to figure out how much current ends up flowing. Because when you connect the transformer to the wall, some current flows, and it makes the magnetism. And then the magnetism gets over to the secondary side, and that generates the voltage for the load. But the load is using some current as well, which means the secondary side is also generating magnetism, which goes back to the primary side. And having all of these variables happening all at the same time would in general be very difficult. But fortunately, we don't have to do that. If all we want to do is relate the two voltages to each other, we can use this idea that the per loop flux is the same on both sides of the transformer. So that means that the EMF of the secondary divided by the EMF of the primary is a ratio that we can calculate. It should be related to the delta flux of the secondary over delta T divided by the delta flux of the primary over delta T. And here, this is the flux of each coil. Now, I said that the easiest way to deal with this is to take the flux of a coil and write it as the number of loops times the flux per loop. So that's where we get to do this. This is the number of loops of the secondary over the number of loops of the primary. And in the top of the fraction, we have delta flux loop over delta T. And in the bottom, we have delta flux loop over delta T. If the primary and secondary share the same amount of flux per loop, then definitely the rate of change of the per loop flux is the same. So basically, the top and bottom of that fraction cancel. And we get the transformer relationship that the ratio of the number of loops is the same as the ratio of the voltages. So that ratio of N secondary over N primary is called the turns ratio. And like I said, usually either the primary or the secondary voltage is something we set. Usually we set the primary voltage by plugging it into a known power source. But sometimes the question is, what power source is necessary? In which case we might be solving for that. So now, what about the currents? We'll use the idea that an ideal transformer is actually a fairly efficient device. It's probably around 85 or 90% efficient, which is fairly good as power devices go. So efficiency is a measure of what you get versus what you put into something, just generally. So in this case, we could write efficiency I usually call it an epsilon because we use the letter E for too many things already. So I'll use the Greek E. Should be the ratio of the output versus the input. So you could be talking about monetary efficiency. If you're running a business and you accept credit cards, then the credit card companies skim off a little bit of the money before you actually get it into your bank account. So for every $100 the customer spends, you only get $96 or $97 or something like that. So that system has an efficiency of about 97%, that money system. And the idea of efficiency works great for energy type things. So this would also be written as the power in the secondary is the efficiency of times the power of the primary. Just by kind of multiplying the P in over to the other side and realizing that the input to the transformer is that primary side of the transformer. So if the efficiency is 100%, then we just have P secondary equals P primary. So now that we know something about voltage and we know something about power, we can say something about current, because the power is created by a voltage driving a current. So if we do voltage secondary times I secondary, that should be equal to voltage primary times I primary. And because we're concerned with power over an extended period of time, we're using RMS voltage and RMS current. And this is average power. And the next formula is all RMSs. So then we can say something about the secondary current. The I secondary is just I primary times V primary over V secondary. So that gives us a way of predicting how much current is used in the secondary versus how much is flowing in the primary. Often we'll write this by getting all of the I's on one side of the equation and then get the V's on the other side of the equation. And this is very similar to the ratio we had before, except it's upside down. So we can kind of just say, okay, let's take the same ratio and just write it as to the -1 power. And that gives us a nice relationship for an ideal transformer to relate the current on the two sides. And remember, that's the exact ratio that is the same as the turns ratio. So let's look at an example. Transformer for a cell phone charger. So we're going to have our power source over here, which I'm writing as a wiggly line with terminals attached to the primary side of a transformer. And the symbol for a transformer is a coil with a couple of bars and another coil right next to it. So this would be 120 volts. And on the secondary side, we might only want 5 volts. And then this is connected to our R, which represents the phone. So this is kind of a simplified version of a cell phone charger. So then we might ask ourselves, if the number of loops of wire in the secondary is 100, how many loops of wire are in the primary? This is the exact kind of question that was on the pre-lab this week, because it's transformers. So then we write out our ratios. The turns ratio is the same as the voltage ratio. And because the transformer is generating voltage, we tend to call it an EMF and use the curly EMF symbol for it. So then we fill in what we know. 5 over 120 is equal to 100 over N primary. And hopefully you can easily see that N primary is equal to 2400 turns. And then we can think about the currents. Typical value for cell phone charging current these days is 1.5 amps. And we can figure out ideally how much is drawn from the wall outlet. So then we'd have I secondary over I primary is equal to N secondary over N primary inverse. I always like to write the fractions as secondary divided by primary. It's like when you calculate a delta, it's the final value minus the initial value. So that way I don't forget which is at the top of which fraction. And I'm consistent mostly about how I write my fractions. So then this would be 1.5 amperes over I primary is equal to 100 over 2400 inverse. So then we can write I primary is equal to multiply that over there, divide that over there, which means 1.5 times 100 over 2400. Oh, good, I did pick the same value. 0.0625 amperes. And then in this case, on the primary side, P of the primary is V primary. I primary is 120 volts times 0.0625 amperes. Is 7.5 watts. And then check the secondary side, make sure everything's working out. P secondary is 5 volts times 1.5 amperes is equal to 7.5 watts. So check. We assumed it was perfectly efficient, and the double check verifies that it was indeed perfectly efficient according to this theoretical calculation. So that's the easy part. Any questions about the easy part? Now let's look at some ways that this could be a little bit weird. Has anybody heard of vampire power? There have been articles floating around about vampire power recently. So the idea of vampire power is our transformers use some power when I secondary is equal to 0. So the secondary is the side with the load. That's the stuff we're attaching. That's the device we want to run. But the transformer still uses some power in that case. And in this case, the primary side acts like an inductor with some resistance. So we might have an L value equal to something like, I'm going to make up a value, 3.0 henries. And I want to have an idea of the resistance. How much is the resistance of 24 gauge wire? It is 25 ohms per 1,000 feet. Let's see. 1 loop of wire is around 1/2 foot. So if I have 200 loops of wire, that's about 100 feet. So then this is going to be R is equal to 2.5 ohms. So this goes back to the AC circuit analysis that we were working on. So it's a way to review. So if we want to know how much current flows in this inductor with this amount of resistance, what we have to do is we have to calculate the X sub L, the reactance of the inductor. the ohms value for that inductor. And this is going to be 2 pi FL, which is 2 pi times 60 hertz times 3.0 henries is 2 times pi times 60 times 3 is roughly 1130, rounded to 3 significant figures, ohms. And then we have both an inductance and a resistance, and the current has to go through both. So they share the exact same current, so they're effectively in series with each other. So we should calculate Z as the square root of R squared plus X squared. So this is going to be the square root of 2.5 quantity squared plus 1130 quantity squared. Which is 1130. So the calculation is true. When you have an X component and a Y component, and one of them is very, very much bigger than the other, then the diagonal of the triangle, the hypotenuse that we calculate here, is basically the same as the stronger component. And anytime there's a ratio of more than around, I don't know, 10 or 20 to 1, you can get away with skipping the Pythagorean theorem calculation and just use the bigger one. Now, if there was capacitance here, you'd have to do the x sub c and subtract the x sub l minus x sub c. You can't get away without doing that. But since we didn't have to worry about any capacitance, all of our reactance came from the inductor. So when we did that calculation and found out that it is so much bigger than the resistor, basically that is the ohms value that we care about. So then this is going to draw some current from the wall. It's not a huge amount of current, but it's going to be some. So we can do V equals I times Z, which tells us I equals, we divide by Z to get I by itself, so divide by Z. So that's 120 volts over 1130 ohms is equal to something. .11 amps. And in this particular example, that's actually a sizable current. So then how do we calculate the wasted power, the vampire power? Well, power is only used by a resistor. And the resistor doesn't have 120 volts across it because there's a resistor and an inductor in series with each other effectively here. So the easiest thing to do is just to take Ohm's law and use it to calculate the voltage of the resistor, and we get I squared R. So then that is the 0.11 amperes squared times 2.5 ohms. 0.11 squared times 2.5 is 0.03 watts. So now I want to find out how expensive this is, assuming we only get charged for this power. I think there's also going to be some inefficiency in the wires in our walls. So that's going to increase the wasted power, but I'm not going to include that in the calculation right now. So power is equal to energy over time. And it's energy that we pay for. So energy is equal to P delta T is 0.03 watts times, we need an amount of time. I like to calculate things for a month because we usually get charged per month by the power company. So a month is 30 days times 24 hours a day. 24 times 3 is 72. Yeah, so 720 hours. So 0.03 times 720 is equal to 21.6 watt hours, which is 0.0216 kilowatt hours. Kilo is 1,000 times bigger, so the number is 1,000 times smaller. And then we can do cost is rate times amount. So our rate is usually around $0.12 per kilowatt hour. And the amount of power we're talking about is 0.0216 kilowatt hours. So we're talking about 0.002 dollars is 1/5 of a cent. So in this example calculation, the amount of wasted power was basically nothing. Does that mean that this calculation is accurate and you should leave everything plugged in all the time? Probably not, because I really did make up some of the numbers there, especially the resistance and the inductance. At some point, I'm going to have to actually measure the inductance of a transformer and the resistance of a transformer wire and see what they are for a real transformer, not necessarily one that, like the lab one that you used this week. But I didn't get those numbers available yet, so I made stuff up. Now, building a 3 Henry transformer takes lots of material. It takes a lot of iron to build that core. It makes it heavy. It makes it more expensive. Could we get away with a, say, 30 millihenry transformer coil instead? Because a millihenry transformer coil is fairly cheap. You can make it small. You can put it inside one of those little cubes that we plug into the wall for our cell phone chargers. And the answer to that is, of course, yes. But the frequency must be higher, because part of our calculation was calculating this X sub L, the inductive reactance. And if we reduce the L value, we have to increase the F. Otherwise, our ohms value, our reactance is going to be lower, and we're going to draw more current, and we're going to have more waste. So modern cell phone chargers start their process of getting energy from the wall by oscillating at a very high frequency, and then that very high frequency is put into a transformer, and the transformer gets to be really tiny, and that allows them to operate more efficiently. So that's just a little detail on kind of the difference between 1970s technology and 2010s technology. We're much better at these oscillators, and as a result, our cell phone chargers are a lot smaller than an equivalent 2.5 amp power supply using 1970s technology. A power supply that would be capable of supplying 5 volts DC, which is what our cell phones need at 1.5 amps or 2.5 amps, would be like a brick the weight of like 4 or 5 books. And we would not want to have to carry that around with us to the airport in order to keep our phone charged. That wouldn't work. People wouldn't do it. So, any questions about that? Cool. Now, on Monday, I'm just not good with this days of the week thing this month. Maybe when we flip over to November, I'll magically know what day of the week it is all the time without having to stop and think about it. On Monday, I asked you to look at the homework and bring in questions about the homework. So what would you like to talk about in the homework? Go for it.
I don't have a question about specifically, but it's the last 2 homeworks that you posted that are
yes.
over exams.
Basically, yes, but I wouldn't discount the information from homeworks 1 and 2 because our physics courses tend to be cumulative. And we're working toward trying to understand light. So everything is building up to talking about electromagnetic waves in about 3 weeks. So yeah, it's a little bit cumulative. There's a little bit less of like the electric fields, probably not a combination circuit with like series and parallel in the same circuit, because that we do with DC only. But the ideas of electric field is voltage per unit length. So electric field is measured in volts per meter. The idea that electric field is generated by charges and pushes charges around, and then DC voltage pushes current. We reuse those ideas here. Absolutely. So what do you have?
Number 5 on homework 4.
Okay, let me take a look at it here. Okay, so I see the question. Help with homework 4-5. Is there something specific that you're having trouble with?
I don't know. I did it a while ago before we actually went over some of this stuff. I know it's got a lot of parts. Maybe just go over the general, because I know everybody's got different numbers. Even if you don't do this one.
So this is R, L, and C. And what we're told is R, L, and C, and V total and F. So one thing we want to do is V total RMS is the given V total over the square root of 2. Whenever we're given a voltage or a current value, we want to check and see if it's an amplitude that's a maximum as an amplitude or an RMS value. And if it's not an RMS value, first thing, convert it to RMS. Do all calculations in RMS. It's easier that way. And then we want, I'm going to label these points here, A, B, C, and D. We want VAB, which is the voltage of the resistor, because between points A and B is just the resistor. So to calculate the voltage of a resistor, we want to do I times R. Okay, so we know R, we don't know I. So apparently we need to calculate I. So we're going to have to use V total is equal to I times Z total. So that means we have to go through the whole process we talked about on Monday of taking the inductor and the capacitor, converting their Henry's and Farad values into Ohm's values. The X sub L is 2 pi FL, the X sub C is 1 over 2 pi FC. So those are formulas that are on the equation sheet. So you got to run through those formulas, get the X sub L and the X sub C. And then you have to subtract those two to get the overall X. And then take the overall X and the R and put them through the Pythagorean theorem to get the overall Z. And then you can calculate the current. So we're talking like 5 steps already. And now we have the current. And that's what I demonstrated on Monday. So now let's look at the things that are specific to this. We want the voltage from A to B. That's the voltage of the resistor. Once we know the current, just multiply by R. We got that value. Okay? What do we want? We want VBC. VBC. Well, between B and C is the inductor. That's V sub L. That's I times X sub L. Well, by this point, we've already calculated I, and in order to calculate I, we had to convert the L into X sub L anyway. So we already have both of those things. We can multiply them and get a value. That part's great. Okay, we want VCD. VCD. That's just the voltage of the capacitor. So that's I times X sub C. I guess I scrolled that off the top of the screen. Okay, so far so good. Kind of model it after the process that I did on Monday for that example circuit on Monday, and it should work out fine. The only difference here is that on Monday, I knew that 2 pi f was 500, and here you know f. So you're going to have to multiply f by 2 pi in order to use the formulas. Now here's the weird one. We want V between B and D. So this is going to be I times the Z value for just the L and the C. Because between points B and D, it's both the L and the C. Now, we know how to calculate the X sub L, and we know how to calculate the X sub C. We know how to calculate a Z if there's a resistor in it. All we have to do this time is calculate the Z without a resistor in it. So this is going to be Z of just the inductor and capacitor is the square root of x squared is just the absolute value of x. And that is x sub L minus x sub C. So to get the voltage between points B and D, you have to take those two reactance values that you calculated a while ago because it was part of the process and subtract them. And that's what you end up multiplying by the current to get the last answer. So what do you think would happen if I wanted the voltage between A and C? That wasn't part of the question, but it could be part of the question. So what's between points A and C? The L is the inductor. I know the letter L is not in the word inductor. I'm sorry about that. So this would be I times the impedance of the resistor and the inductor. And this is just like what I did for the vampire power on the previous page. So we would calculate the Z of the resistor and the inductor as a Pythagorean theorem with R squared plus X squared. And here, X is just X sub L. And X sub L is something we had to calculate a while ago in order to figure out the Z, to figure out the current. So we have it. It's up the page somewhere in our work. So we just take that X sub L by itself without the capacitor, combine it with the resistor, then we get the impedance between points A and C. And like I said, that last line wasn't part of the question, but it could be part of the question.
Well, if you're combining a resistor and an inductor in series, you do the Pythagorean theorem. But if you're doing a capacitor and an inductor, you do the XC minus, or the XL minus XC.
Right. The inductor and the capacitor cancel each other out first. Then whatever X you have goes together with whatever R you have in the Pythagorean theorem. Yes. That's the series impedance process.
What does a resistor and a capacitor do?
The resistor and the capacitor would do the same thing. So I'd have to rearrange the circuit to get a resistor and a capacitor, but they would do the exact same thing. So you'd get an X value for the capacitor, the reactance of the capacitor, and the resistance and Pythagorean theorem together.
Okay, so it's only if you have an inductor and a capacitor that they can.
Right. It's like adding vectors where the inductor is up, the capacitor is down, and the resistor is sideways. So if you have all Y direction, then you just take the pluses minus all the minuses and you're done. If you have all X direction, it's just the X value is the length of your vector. It's when you combine X's and Y's that you end up with a diagonal vector that you have to use the Pythagorean theorem to find the length. So fill in a couple of the gaps here so it's in the notes. Z is equal to square root of R squared plus X squared, and then X is X sub L minus X sub C. And the X sub L and X sub C are things we have to calculate along the way. Any other requests for hints? Now, if we get to Monday, our review day, and you're still stuck at that question, then I can go through it again in more detail. But I like to start by giving a hint and let you go and work on your own first, because really, I'm not here to do everything for you. I'm here to try to help you become self-sufficient. That's what I want. And if I see everybody working and being self-sufficient, then I'm really happy. Then I'm in a good mood when I write the exams, and then the exams are doable, and you all get good grades, and everybody's happy.
Yeah, they have on the homework where you can do it with different numbers, and it'll like show you how to do it, but with different numbers. So I did it, I just didn't know like why.
Yeah.
So.
Well, really, we're trying to figure out how to use a current times something to get a result. A current times an impedance gets us a voltage. And which voltage it gets us depends on which impedance we use. If we use just the resistance, it gives us the voltage of the resistor. If we use just the impedance of the inductor, then it gets us the voltage of the inductor. But if we have two things in series, then we have to find their combined impedance, possibly by the Pythagorean theorem. Now, in this case, for that voltage between B and D with the inductor and the capacitor, we basically go through this impedance process to find the overall Z, except we don't have an R. And that actually makes the process a lot easier because all you have to do is subtract and ignore the minus sign. That's absolute values, you just ignore the minus sign. So these voltages that are being asked about are things that we could measure in a lab. We could set up this circuit, put a signal generator on it, and actually go and measure these things. And hopefully, I think, we'd see values very similar to this. For the inductors, we would use the magnetic coils that you used with the magnetic field sensor that you had to shove inside and figure out how much magnetic field was on the inside. And it came out to 0.0039 for everybody because you used the same coils with the same voltage. So the rest of getting ready for the exam is mostly just practice. Going through the homework, getting some answers. Absolutely feel free to send me questions as you're working on the homework. If you're in WebAssign, every question has that ask your teacher thing, and I try to respond to those like twice a day, once in the evening and once in the morning when I wake up. So if you do have a question on something, if you're stuck on something, send that ask your teacher question and then move on and work on the next thing, because you may find 4 more things you need to ask questions on. And you don't want to wait for this half-day exchange 4 times in a row, because then it'll be exam day before you're actually getting done. All right, so on Monday, we'll review. We'll go back to magnetism. We'll do some right-hand rule reviews. Should we do one right-hand rule example before we go home for the weekend? We probably should. So one more thing. Right-hand rule review. Yeah, that's a good idea. So let's say we have electron is moving northward and we want the force to be upward. What magnetic field do we need to do that? I haven't done it yet. I agree. So one of the reasons I picked these particular directions is to stress again that north and up are not the same thing. So if a description uses the word north, that says we're using mapping coordinates, which means up is towards the sky and north is towards the top of the map. So the electron's moving northward. That's our first finger. We want our thumb, the force, to be upward. That's out of the page, which makes our middle finger point west, but it's an electron. So after we do the right-hand rule, we flip our answer because it's an electron. So the answer is east, just like the man said. Great. Or, absolutely, electron, use the wrong hand. Velocity is north, force is out of the page, and magnetic field is eastward. I call it the wrong hand. It's not the right hand, it's the wrong hand. Yes. I write with my wrong hand all the time. All right, so there's the description of where everything's pointing, and at the end we flip because electrons, so our B ends up pointing the other way. All right, so go forth, work on your lab reports, and bring in lots of questions on Monday, and I will do my best to make all of the answers as clear as possible.